All right, this is AP Calculus with Sparks. This is day 48, and I think maybe this looks a little bit notational heavy, but really it's not that difficult as what may it look like. So this notation looks like a kind of a very skinny, long capital X. S is called an integral. So the integral of f of x dx, this is the antiderivative of original function, f of x. When it doesn't have limits, this is called an indefinite integral because there is no limiting factor. We're looking for the antiderivative for the whole entire function. However, if there are limits, stop that, limits like this from a to b, then we only want a definite integral, and we only want the piece between a and b. And this represents the area of the curve underneath f of x and the x-axis between a and b. So again, this may look a little difficult and a little confusing, but I think we're going to be able to get you right through it. So we're going to look at 4 different Riemann sums: left hand, right hand, midpoint, and trapezoidal. If you had watched the other video I had up, then you've probably already seen some of this. We just didn't really attach it to antiderivatives and calculus. So this day in class has lots of pages, and a lot of it I'm going to let you do on your own. I'm just going to pause the video and give you the answer because it really is just finding the area of rectangles, which I know you can do on your own. But this one we're going to do together. Okay, so this is the function -1/3 x squared plus 2x plus 5. And we're looking at the interval from 1 to 7. So we're going to divide it from 1, that's here, to 7, that's here. And we're not going to worry about anything except for what is in between 1 and 7. And we're going to divide it into rectangles of length of 2 units. So from 1 to 3, that's going to be one rectangle, and from 3 to 5, that's another rectangle, and from 5 to 7 is our third one. And we're going to use the left-hand vertex of each rectangle. So I go to the left, and from here over, that's the height of that rectangle. Left and over, this one goes a little bit outside of our function. So does this one right here. So this is the area we're going to calculate to estimate the area underneath the curve between 1 and 7. So area of a rectangle is equal to base times height. Our base for each rectangle is the same length. We were given that it's going to be 2 units, so the base is equal to 2. And then the height is going to be equal to the function at each one of those values, and we're calculating from the left. So the height is going to be f of x, where x is equal to 1, 3, and 5. So the area of the first one is going to be 2 times the height, which is f of 1, which we can plug into -1/3 x squared plus 2x. The area of the second rectangle is going to be 2 times f of 3, because that's this height over here. And then the area of the third rectangle is 2 times the function value at 5. So this one's going to be 2 times f of 1. So f of 1 is -1/3 times 1 squared plus 2 times 1 plus 5. So that's equal to 2 times 6 2/3, which is equal to, let's see, 12, 13. And 1/3. I'm going to let you do area for the second and third rectangle and check your math. So I got 13 1/3 for the first one, 16, and then 13 1/3 for the third one, which gives us, what is that, 26 2/3, so 26 plus 16 plus 2/3 is 30, 42, and 2/3 for that definite integral. So next page, we're going to approximate using left-hand Riemann sums, which is all we're doing is adding up the area of the rectangles, that's a Riemann sum, with an interval of length 1 unit. So we already did it with 2 units. 2 units, we got our area to be approximately 42.66 or 42 2/3. Now we're going to do the same thing, left hand again, but this time 1 unit. So go ahead and divide that into rectangles with 1 unit, and then, so pause it now and do that. So it should look something like that. Again, going from the left, so you start on the left and move over like so. We have a couple of extra ones that are a little bit too big, and we have ones that are too small. So we're going to calculate that area. We need to find the area of, this time, 7 rectangles. So area of the first one is going to be equal to 1, because the width is 1, times the function at 1, so on and so on. Area of 2 is equal to 1 times f of 2. I'm going to let you work that out. We're going to get all 7. Actually, I said that 7 twice, but there really is only 6 because we're not starting at 0, we're starting at 1. So here's 1, 2, 3, 4, 5, 6 rectangles. All right, go for it. Pause it now. All right, so I found the area of each one of those individual rectangles, and I forgot we're learning notation. So the integral from 1 to 7 for this function is approximately equal to, well, the area of each one of these added together, and that was actually 1 for the width times f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5 plus f of 6. And then we would add up all of those pieces, which I am not going to do just because it's just arithmetic, and you should be able to do that. So let's take a look at taking the same function, but this time we want rectangles with units of half a unit. So instead of these are units of 1, we're going to have to cut that in half. And these are going to be our rectangles. So go ahead and draw that picture, and then we'll set up the problem. So this time we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 rectangles. So we're going to set it up. You can go ahead and find it on your own, all the little pieces, but the function from 1 to 7, the integral of f of x dx is approximately equal to, well, this time the width is 1/2, so 1/2. If I distribute it, I get 1/2 times each one of those, but I'm going to put the 1/2 on the outside to save time and space and effort and energy. So we got f of 1, oops, nope, that should be 1/2, plus f of 1 plus f of 3/2 plus f of 2 plus f of 5/2 plus f of 3, etc., until we get all the way to f of 6.5. 13/2. And that's how we would set that up. So you can go ahead and perform the arithmetic and then check your answer. I'm going to give you the answer, so pause it. So adding up all 12 rectangles, multiplying that by 1/2, because that was the width, I got about 40.917. On the next page, let's look at right-hand Riemann sums. So this time we're going to start from the right-hand edge of the rectangle and move to the left. So, and we're going to go with 2 units. So we started with 2 units, then we went with 1 unit, then we did ½ a unit, and now we're going back to 2 units from the other side. So again, we're still going from 1 to 7. We're still going to draw our rectangles. But instead, when we do our height, we're going from the right endpoint. So it's easier for me to start on the right-hand side and go over. And go to the top and the right-hand side of that rectangle and go over. So this is what it looks like from the right-hand side. So to set that up as an integral, we have the integral from 1 to 7 f of x dx, which is approximately equal to the area of those three rectangles. And the width of those is 2, so 2 times the height, which is the value of the function for the height. And we're starting with f of 3, right hand. So f of 3 plus f of 5 plus f of 7. That's our last one right there. When you calculate the area of those two, or those three, and then you multiply it by 2, I'm going to give you the answer, so pause it if you want to wait. It's approximately equal to 34 and 2/3, or 34.66666666. So now we're going to do right hand with 1. So go ahead and draw those rectangles and check back with me. So pause it now. So it should look like that, going from the right, 7, 6, 5, 4, 3, 2, back to 1. Now see if you can set up the integral, and then we'll go to calculating. So go ahead and set up the integral from 1 to 7. See if you got your right. So pause it now. So the integral from 1 to 7 of f of x dx is approximately equal to 1, that's our width, times the values of the function starting at 2, f of 2, f of 3, f of 4, all the way to f of 7. So for the sake of redundancy and making this video 3 hours long, you go ahead and do the next approximation, right-hand sums with the interval of length 1/2 a unit. So you can pause it and do that. And then we'll work on midpoint. I'll do one of the midpoint and we'll move from there. So pause it so you can do approximation number 6. So you should have right hand with 1/2 intervals from 1 to 7. And this is a really good question. So I'm going to let you think about what kind of inferences you can make about the approximations as the lengths of the rectangles decreases. Now we're talking about the width there. So we had 2, we had 1, we had 1/2. What can you conclude? Put your answer right here, pause it, and see if you said something similar to what I'm going to say. So hopefully you came up with something that said as the width of each rectangle decreases, the approximation gets better, or the more rectangles we use, the approximation gets better. And for some reason that has to do with we have less area that's outside or over the function, and less area is left out when we calculate the area of the rectangle. Midpoint Riemann sums. I'm going to help you get started, but you're going to do most of these approximations of midpoint by yourself. The first one, length of 2 units, we're going from 1 to 7. So we have at 3 and at 5. Now when we went from the right hand, we started here, and when we went from the left hand, we started here. But this time we want the midpoint. So we want to know, halfway between 5 and 7, where's the function height at? So we're going to go with the height at 6. We're going to go with the height at 4. And we're going to go with the height at 2. So we're going to do from 1 to 7, f of x dx, and that's going to be approximately equal to, well, the width, again, is 2. 2, and instead of f of 1 or f of 3, we're going to use f of 2. f of 2 plus f of 4 plus f of 6, like that. So go ahead and calculate that, and then I'll help you get started with 8. So go ahead and pause it now. So I got 40 and 2/3, 40.666. All right, this time we want intervals of length of 1. So from 1 to 7, and intervals are 1, so we can draw this. but our height is going to have to be at the half mark. So at the half mark, the height is here. And at 2.5, there's our height. And at 3.5, and at 4.5, 5.5, 6.5, something like that. So the integral from 1 to 7 f of x dx is approximately equal to, well, our width is 1, times the function at 1.5 plus the function at 2.5 plus the function at 3.5 plus the function at 6.5. So make sure you're saving these values. We're going to put them in a table here in just a minute. Some of you are probably already wondering this. Why are we using rectangles? It looks like there's better shapes that would average out a little better. And we're going to do trapezoids, which you'll definitely see look like they modeled it a little bit better. So from 1 to 7, we're going to do, again, 2 units from 1 to 7. 2 units wide. Wow, my drawing is getting worse. Like that. But instead of going from right hand or left hand, we're just going to draw those together. Where did you go? Let's see if I can find it. Uh-oh. Click here. So sorry about that. Touchscreen is a little sensitive sometimes. So we're going to go endpoint to endpoint. And those are trapezoids. So you may have forgotten the area of a trapezoid is equal to 1/2. And then we've got base 1 plus base 2. And then we have that times the height. I think I was going to try and write that base 1 plus base 2 over 2 times the height. That's why I made it look so funny. So base 1, this would be base 1. This would be base 2. And this is going to be h. So for area of each of these, it's going to be equal to 1/2. And then our height, which is 2. And our base 1 is going to be f of the first part, so f of 1 plus f of 2, so that would be our first rectangle. The second rectangle would be 1/2 times the height, which is 2, and it's going to be f of 2 plus f, nope, it's not 2, is it? Those should be 3, sorry, our width is 2. F of 3 plus f of 5. And the third rectangle is 1/2 times the height, which is 2, times base 1, which is f of 5, plus f of 7, which is base 2, and that is how we would calculate the area of each of those rectangles. So we could say that the area from 1 to 7 of f of x dx could be approximated with, well, the width. We could factor some of these out, right? Because we would sum all these together. So we have 1/2 times 2. That's weird, that a2 disappearing like that. All right, so then we've got, well, we have 1 f of 1. And then notice there are 2 f of 3s. And there are 2 f of 5s. Plus 1 f of 7. You could calculate each one of these individually. I'm just looking for ways to shortcut stuff a little bit. So this is actually, those cancel, right? So we just have 1, and then you calculate each one of those function values. And any way you look at it, you should get something around 38 2/3. So you go ahead and do it for number 10. These each have a height of 1 unit. So there should be 6 of them again. Okay, pause it, go for it. So the integral from 1 to 7 of f of x dx can be approximately equal to 1/2 of f of 1 plus 2 f of 2's plus 2 f of 3's plus 2 f of 4's, etc., and then 1 f of 7. And I got 39 2/3. So remember how I said save all those numbers? We're going to put them into the table on the next page. So the first one, left-hand Riemann sum, interval of 2, interval of 1, interval of 1/2. Right hand, go find those and fill this out right now. So gathering up all the areas of all those ones we just did, this is what I got. The question though we really want to ask, do you think each one of these is an over or under approximation for the area? So you might want to go back and look at the picture and see what area is shaded in and make a judgment. Is this over or is this under? Pause it right now. I'm going to fill in what I think. So based on my pictures, this is what I got. Over, under, under. So we're going to leave this other space empty until after the next lesson. But would you go ahead and put a star next to the ones you think are the closest to the real area, and then we will come back to this in the next lesson. Alrighty, I will see you soon. Bye.